Okay, so let's take a look at determining the intermolecular forces of a molecule. In this case, the molecule here is CH3Cl, which is another name for chloromethane. And what we're going to do here to determine the intermolecular forces, which are the forces between molecules, right? So inter basically means between, right? Molecule forces, so forces in between molecules. We're going to do this step by step by first finding the Lewis dot structure, then generating the Vesper structure, and then we're going to look at electronegativity differences to determine the incidences of the creation of dipole moments, right, which is an indicator of a polar covalent bond. And if anything, we're going to see if a dipole is created, which is another name for a polar molecule. So let's start with the Lewis dot structure. So before we consider the Lewis dot structure, what we can think about here is we think about this species. We have three major different atoms of note. We have a carbon atom, we have a hydrogen atom, and we have a chlorine atom, except there is three hydrogen atoms. Okay. One way we can organize this is we can generate a table to first look at the valence electrons. But before we do that, the first thing I'm going to look at here is determining my central atom. And the central atom tends to be the least electronegative species, right? So it's usually carbon. Now, in this scenario, the electronegativities, we can figure this out using a chart. We're going to use these values later anyways. The electronegativity of carbon, I'm going to use 2 decimal places, so it's 2.55 according to the chart I'm using. The electronegativity of hydrogen is 2.20, right? And these values can differ depending on the values that you were given. And the electronegativity of chlorine here is 3.16. Okay, so you can tell here that hydrogen is the least electronegative atom, which means that it's the most electropositive atom. But hydrogen is too small to be a central atom. So if hydrogen is present, then we look at the second lowest electronegative atom, right? So in this case, it's going to be carbon, and it tends to be carbon if it's present. So carbon is your central atom, right? So in this case, carbon is a central atom. And what we're going to do now is generate a table to organize a few parameters. Okay, the first thing I'm going to look at is the valence electrons of each. Okay, so we have carbon, which has 4 valence electrons, hydrogen, which has 1, but because there's 3 hydrogens, I'm going to put times 3 here. We also have a chlorine atom, which is a halogen, so it should have 7 valence electrons. And what we're going to look at are 2 parameters, which is going to help us to determine the total number of bonds we should see in our Lewis dot structure. We're going to be looking at the total number of electrons that is present in the stable octet and the total number of electrons in the valence shell. Okay, or we can look at it as the total number of valence electrons. Okay, so in carbon, we have, to form a stable octet, it's going to have a total of 8 electrons. For hydrogen, to form a stable octet, it's going to have 2 valence electrons, but because there is 3 hydrogens, I'm going to multiply this by 3, right? For chlorine here, you should have 8, as well as similar to carbon. And a total number of electrons that you should see in your stable octet, because remember, the goals of atoms when they are, or the goal of elements when they are essentially reacting and bonding, is that they want to form a stable octet. That's the whole reason why they react, right? Otherwise they wouldn't do it because it requires a lot of energy. So if we add up all of this column here, the TES column, total number of electrons in the stable octet, we get 8 plus 6, which is 14, plus 8, which is 22. In the next column, this is the total number of valence electrons, or total electrons valence. I just abbreviated it as TeV. And in this scenario, carbon, we can notice here, has 4. Each hydrogen has 1, but there's 3 hydrogens, so we're going to do 1 times 3. And the chlorine here, it's going to have basically a total of 7. Okay. If we add up this column here, we have 4 plus 3, which is 7, plus 7, which is 14. Now, using these values that we've generated, what I'm going to do is use this formula. The total number of bonds in a structure, and you have to note here, guys, that this formula works as a generalization. It doesn't work in every scenario, because we can imagine that this is only for structures that actually follow the octet rule. Not all structures will, because remember, the octet rule is a guideline, but it's pretty useful excuse me, it's pretty useful because it's a great guideline or a great foundation to work on, to build on. And it's very similar to us teaching you guys the Bohr-Rutherford structures, because that is also a very good model to view the atom and molecules, right? So the total number of bonds is equal to the total number of electrons in the stable octet minus the total number of valence electrons, and you divide this by 2. So this is the formula. So let's plug in those values. Okay, so in step 3 here, total number of electrons in the stable octet. To make a appropriate structure here, we need 22 electrons to make sure that every atom satisfies, or each element satisfies, a stable octet. 22 minus 14, and we're dividing this by 2. So we basically get 8 over 2, which is 4. So this structure we should expect to see 4 types of bonds. And before we actually look at how this bonding architecture works, what we can do is we can think about a potential rearrangement, right? So potential rearrangement, right? If we think about a potential rearrangement, right, we can put carbon, which is the central atom, in the middle of the 3 hydrogens and the chlorine, right? You can imagine that hydrogen only has 1 valence electron, so the most it can form is 1 bond. We say hydrogen is monovalent because it can only form 1 bond, right? And each hydrogen will follow suit. Chlorine is a halogen. It only needs to form 1 bond, so we can also say chlorine is going to be monovalent. And this is a potential structure because we know that carbon should be tetravalent. It should have a total of 4 bonds, right? So in terms of our Lewis dot structure, let's call this step 5. In terms of our Lewis dot structure, I'm just going to kind of denote carbon in navy blue here. Okay, so carbon has 4 valence electrons. It's going to share 1 with each hydrogen. So each hydrogen, I'm going to use dark red here, should be able to donate 1 valence electron. Okay, and then you have basically a complete satisfaction of the octet rule for each hydrogen. And then chlorine also needs an extra electron to form a stable octet, and it's going to share 1 to gain carbon's electrons, as shown here. So now you can see here that chlorine has access to these electrons. Each hydrogen will now have access to these electrons. Okay. And the carbon here in the center should have access to all of these electrons here, right? So now our octet rule is completed, right? And you can actually see that it's basically the same structure we generated. Now this is all good and well, but the other thing here is that, right, you can see that if we change all of the bonding electrons, which are the ones in the circle here, so here, 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 these are all bonding electrons, right? We could just change them to single bonds. A single bond is basically a pair of bonding electrons. A double bond is 2 pairs of bonding electrons. A triple bond is 3 pairs of bonding electrons. And how this formula actually kind of works here is that a single bond counts as 1, a double bond counts as 2, and a triple bond counts as 3, right? So what the total number of bonds represents is the pairs. It's the total number of pairs of bonding electrons. So this is 1 pair of bonding electrons, a double bond is 2 pairs of bonding electrons, and a triple bond is 3 pairs of bonding electrons. Now this is all good and well, but if you take a look at the structure, this is not what the actual structure will look like, right? It doesn't have 90-degree bonds. So this is a structural diagram, but we want to look at its actual 3-dimensional model, right? And this is where we have to actually look at the Vesper model. Well, what Vesper stands for is the valence shell electron pair repulsion. It's a 3-dimensional geometry of the molecular shape. So what we need to understand here is the total number of bonding atoms, lone pairs, and from this we can figure out the total number of electron groups. Now the number associated with the electron groups is also given another number, another value. It's called the steric number. But this is how we're going to be looking at it, right? And the total number of electron groups that surrounds the central atom is equal to the bonding atoms plus the lone pairs. Okay, so if you don't understand this too well, I'm going to tag the introduction to VSEPR Intermolecular Forces at the end of this video. It's basically a giant overview of this topic. You can learn it from scratch, although it's a very long video, I would suggest just going through bits and pieces of it. But it's there if you want to kind of review some of these concepts, right? These questions are just meant for you guys to try and practice. Also, give these questions a shot, and then actually, pause and rewind and fast forward and verify your solution and your procedure, right? So after we've done this, now what we need to do here is think about, okay, how many lone pairs does our central atom have? Well, it's very clear when we view the structural diagram. There is 0 lone pairs. How many bonding atoms does our central atom have? Well, it's 1, 2, 3, 4 bonding atoms. And the total number of electron groups is the sum of these two, so it's 4. Right? And this is what I call the shorthand notation, but it's a great way to memorize some of your Vesper structures. So this value here is actually associated with the tetrahedral geometry as well as shape. Okay, so it's the tetrahedral geometry and shape. And what that should look like, according to our Vesper structure, there is the carbon central atom here, right? There is a hydrogen here, hydrogen here. All right, let's put the chlorine that's coming out of the page here, right? And there is also a hydrogen here. Okay, there's free rotation associated with single bonds, so you can actually place these any way you want. But there is a different type of isomer of these molecules. They're called they're types of stereoisomers. They're called enantiomers, which you might actually come across in your future study of chemistry, where they're not exactly the same. But that's not part of this lesson itself, right? So don't worry too much about that right now. So this is basically the structure. And we know this is a tetrahedral geometry, so the angle associated with that is 109.5 degrees. Okay, so now we have the structure. We need to figure out if this molecule is polar or nonpolar. Well, if we can do that, we can then figure out the intermolecular forces that are found in this molecule. So one way we can actually do this, I'm going to redraw the structure here so we can kind of work with that. Right, and you can try to visualize this in 3 dimensions, guys. Right, but if you were to visualize in 3 dimensions, think about a plane, like a flat surface, like a page. Okay, sorry. Let me just make that look like a flatter surface. Okay, so let's say this is a plane, right? So what this basically means is that, there is 2 bonds in the plane of the page are on the flat surface. One of the bonds is coming out of the flat surface, which is shown by the darker wedge here. And the other bond is going into the page, right? It's kind of like poking a hole in the page, is going below the page, and it's there, right? And this angle here is 109.5 degrees. And each angle, actually, if you were to measure it, should be 109.5 degrees. Like this angle here would be 109.5 degrees. Okay, it's not too clear. If you wanted to visualize this better, I would recommend getting a molecular kit, right? So you can use ball and stick model of molecules to kind of visualize this in real life. Okay, so now that we have the molecule, what we need to do is assess electronegativity differences. So for assessing electronegativity differences, what we're doing is we're going to look at the differences between the different types of bonds you would see in this molecule. Now there's only really 2 types of bonds that you'll see. You'll see one bond here between the carbon and the chlorine, and the other bond here is going to basically be between the carbon and the hydrogen. Yeah. So let's find the electronegativity difference between the carbon and the hydrogen. So you can kind of refer back to these electronegativity values that we posted here. So let's use these values here. Right, so if we're calculating this, we'll do the calculation and we'll just use black here so you can see it better. So if we do the electronegativity difference between carbon and hydrogen, we're basically finding the absolute value, because we're just looking at the magnitude, between carbon minus hydrogen, which is basically a value of 2.55 minus 2.20, and that's going to give us a value of 0.35. Okay, now what does this difference tell us? Well, we need to actually look at a scale, and the scale I'm going to give you guys, and this might be different from what your teacher's giving you, but I'm going to use 2 decimal places. If the electronegativity difference between 2 atoms that form a covalent bond, or any bond really, right? If the electronegativity difference is greater or equal to 0, but less than or equal to 4.5, then this is going to represent a non-polar covalent bond. If the electronegativity difference is greater than 0.45, but less than 1.7, this represents a polar covalent bond. Okay, so what's the difference here, right? I'm going to use NPCB for non-polar covalent bond and PCB for polar covalent bond. Well, a non-polar covalent bond is where you have symmetric or equal electron sharing, that the electrons are actually found in approximately the same distance between the two atoms, okay? When you have a polar covalent bond, there is asymmetric electron distribution, or asymmetric or unfair electron sharing. The electrons are actually found closer to the species that has a higher electronegativity. And what that really means is electronegativity is really how strongly an atom can attract a pair of electrons, external electrons, right? So higher the electronegativity, the more a species can actually attract electrons, right? So based on this information, we can tell that this is basically a non-polar covalent bond. Oops, I don't know why I changed the brackets there. Okay, so that's the non-polar covalent bond. So when you have a non-polar covalent bond, we have equal electron sharing, and we don't actually create a dipole moment. Let's take a look at the other calculation. So let's take a look at the electronegativity between carbon and chlorine. Right, so in this case, we're doing electronegativity of chlorine minus electronegativity of carbon. If we look at the values here, right, chlorine here is 3.16, carbon here is 2.55. If we calculate this value, should give us 0.61. So according to our scale here, according to this interval, we can tell that this is a polar covalent bond. So that means that a dipole moment is generated. And what is a dipole moment? Well, we're going to indicate it with this arrow here and the symbol mu. What does arrow show? This is what a dipole moment will show as. And the tail end, which is this portion, so the tail end of the dipole moment basically shows the least electronegative species, or it'll tend to show where the electrons are basically furthest away from, and the tip end of this dipole moment here will show the more electronegative species, the higher electronegative species. It's where the electrons are going to go towards. So in this case, because chlorine has a higher electronegativity value than carbon, then we're going to draw a dipole moment here. So because the electrons are closer to the chlorine, we use the symbol delta to show that there is a partially negative charge at the chlorine. So this is delta negative, partial negative at chlorine, and at this point here we write delta positive to show that there's a partial positive charge from the carbon because the electrons are further away. Now this dipole moment itself is a vector quantity, so that tells us that there is a magnitude as well as a direction. The length of the dipole moment will show you the electronegativity difference. So what that means is if you have a longer arrow, right, like if you had two arrows that looks like this, right, this is vector arrow 1 and dipole moment 1 and dipole moment 2. Dipole moment 1 will have a higher electronegativity difference than dipole moment 2, although they are still pointing in the same direction, right? So based on that, what we can understand here is there is this dipole moment being created. And because this dipole moment gets created, you can see that this molecule now is regiospecific to having opposite charges. So what I mean by that is there is essentially a charge separation in the molecule, and one part of the molecule itself is going to be negative, the other part of the molecule itself is going to be positive, right? As long as the net dipole moment, which is the sum or the vector sum of the dipole moments, is not zero, then you have a dipole molecule. Another name for a dipole molecule is a polar molecule. Okay, so we know this is in fact a polar molecule. So now that we know that this is in fact a polar molecule, well, what kind of intermolecular forces would we expect to see? So I'm going to make some space here just so we can kind of work with this. So let's get rid of this table here. You can imagine that, it does take a little bit of time to go through the steps, but once you guys can understand these steps and working your way through them, then you can basically tackle any sort of problem associated with this. So the intermolecular forces we would expect here, like all molecules, this should have London dispersion forces, right? And remember that the larger the size of the molecule, the greater the London dispersion forces, because larger the size means there's a larger surface area, and because London dispersion forces are contact forces, the more surface area there is, the more you can have contact, right? There is also dipole-dipole forces because we know this is a polar molecule. Now we wouldn't expect there to be a really strong form of dipole-dipole forces here because, which basically constitutes hydrogen bonding, because hydrogen bonding only exists between species, the three most electronegative species, nitrogen, oxygen, and fluorine, which are not found in this species. So if you wanted to kind of visualize how these intermolecular forces would play in this molecule, let's say this is one of our chloromethane molecules. Okay, I'm going to draw that in purple here. And there's another chloromethane molecule nearby, or adjacent to it. Do this in green. Okay, I'm keeping the stereochemistry relatively the same. The stereochemistry is just associated with the three-dimensional arrangement of the atoms, right? So you can have the same constitutional atoms, like the same types of bonds, but you could have different arrangements in three-dimensional space. Now, in this scenario, we can notice here that we have, according to our dipole moment that got created, right? So we would have a dipole moment created here. This is partial positive, partial negative, same idea here, partial positive, partial negative, and the law of electrostatic attraction states that positive and negatives will attract. So essentially, you should have a force of attraction. Whoops. Sorry, guys. So the force of attraction occurs here. This is essentially what a dipole-dipole force is. Now, we wouldn't expect hydrogen bonding, so the only intermolecular forces you would see are these two. Okay, so that's basically our procedure here to assess the intermolecular forces between or found in a molecular structure. So you can imagine that this whole process is a little bit tedious, but it's very important to understand some of the steps that are associated. Right, we'll call this step 8, and you can kind of visualize that here actually. Okay, so what I would recommend here, if you guys don't understand some aspects of this, take a look at the introductory video of Vesper structures and intermolecular forces that I'm going to add to the end of this video. It is a pretty long video, but you guys can pick and choose certain aspects of it or certain portions of it that you can access. You don't have to go through the entirety of it. Okay, so stay tuned for some more questions, guys. Thanks for your patience, and good luck with your chemistry ventures. Congratulations on finishing the video. To reward your attention and determination to learn and enhance your skills, we've created a new reward system this year. Each time you complete a video, you will be rewarded IQ points. Depending on the length, difficulty, and type of video, instructional versus question-based or both, you can be rewarded different levels of IQ points. These IQ point rewards will be either 10, 20, 50, or 100 points. Our goal for implementing this system is to enhance your motivation and improve your daily productivity. Use the amount of IQ points you earn each day to reinforce and gauge your commitment towards your education. And while you do this, remember to like, comment, subscribe, and share our videos. Your continued support will assist us to release more free educational content in the future. Our collective goal at Course Concepts is to assist you towards academic success, one step at a time, because success starts with a single concept. So we want to thank you for being a member of Course Concepts.